In this video, we're going to be looking at Chapter 12, the normal distribution for Math 142. This video will cover the standard normal curve, and then we'll start talking a little bit about z-scores, how to compute them, and what they mean. So the standard normal curve is a way to sort of put all different kind of normal curves and be able to compare them more easily, sort of similarly to the way that we use percents when we talk about, let's say, a score on a quiz or a test in a class. Your teacher can tell you got 14 out of 16, but if you want to compare that to the next quiz that you take that you got 17 out of 20, it's hard to compare them unless they're on sort of the same scale. So we turn them into percentages and it's easier to compare. So we're sort of doing a similar thing with a standard normal curve. We can take any normal curve. I'm going to draw a quick little sketch here. And instead of using the exact numbers, we're going to say that this right here in the center, our mean in the standard normal curve, is going to always be 0. And then we'll do our standard deviations to the right. So this will be, in the standard deviation for a standard normal curve is 1. So from the mean we add 1, we add 1 again, we add 1 again. And then we go the other direction, we subtract 1, and subtract 1. So those numbers down at the bottom of the standard normal curve are what we call our z-scores. So if you were to think of like laying one of the previous standard curves on top of this and sort of seeing where a data point lines up, that's what we're going to be talking about using this idea of a z-score. So here's our definition. A z-score is the number of standard deviations that an x value is from the mean. So if you looked at your data values and you had a data value that falls right here, that data value would be 1 standard deviation above the mean, so the z-score would be 1. So the z-score formula is as follows. So z is equal to the data value minus the mean divided by the standard deviation. And as always, when we sort of start with these big ideas and it seems a little bit abstract, if you're not totally sure that you're following what this standard normal curve means and these z-scores, as we get into some of the application problems, give yourself some time to soak it in there, and hopefully, if it's not quite clicking just yet, it'll start to have a little bit more meaning. So the other way you can write this, and the way you might see it written out, or I might write it in the notes at some points, is that we can use z is equal to, and this is just using notation instead of symbols and things instead of words. So z is equal to x minus mu, again that's our mean, over sigma there, our standard deviation. So you want to note when you're finding z-scores pretty much will almost always lie between -3 and 3, because what we know about the standard curve and about data that falls onto a standard distribution is that it's really rare for data to be out here past +3 or past -3. So if you're computing computing a z-score and you get something greater than 3 or less than -3, it might be time to take a look at your computation, make sure that something didn't go awry there, because those are going to be very, very unlikely. It's possible. So if you get a 4 for a z-score, it doesn't mean you're absolutely wrong, but you might want to just look at your data and think about it for a minute and think about how spread out that data is and if that score does actually make sense. So again, a score above +3 for your z-score or below -3, very, very rare. So let's take a look at number 7. Consider the standard normal distribution. So using that picture we just drew up at the top, the mean is always going to be 0, and the standard deviation is always 1. So let's take a look at 8. What is the z-score of x equals 12 if it is 2 standard deviations to the right of the mean? All right, so you don't have to do any computation here at all. All you need to do is read what it says here. They're talking about something that's 2 standard deviations to the right of the mean. Those are the 2 important pieces of information there. go back to our definition of z-score. A z-score is the number of standard deviations that an x value is from the mean. So this is telling me this value is 2 standard deviations, and then we have to pay attention here so we know the sign. So to the right of the mean. So 2 standard deviations to the right of the mean means the z-score is positive 2. It's right there in the definition. Number 9 asks, what is the z-score of x equals 9 if it is 1.5 standard deviations to the left of the mean? So same idea here. That is telling us, this part doesn't even matter to us. We don't need to know about the value of the actual data value. We just need to know that it's whatever it is. If we were to draw this curve, x equals 9 would be 1.5 standard deviations to the left. So this is important now to realize we're moving to the left. So our z-score is going to be negative 1.5. And z-scores can be decimal values. You're going to see that as we move through the examples and things. It's not just -3, -2, -1, 1, 2, 3. It can be anything in between those. All right, so for the next couple examples, we're going to use that z-score formula. I'm also going to draw a little picture so that hopefully for those of you that are a little more visual, that's kind of how my brain works, maybe you'll be able to see the answer a little bit as well. Excuse me. So suppose a variable is normally distributed. We have to have that be the case, so that's just setting us up, letting us know we're allowed to use this formula, with a mean of -1 and a standard deviation of 2. So this is our mu here and our standard deviation here. So there's my x value is 2. So the formula up here, I'm going to just scooch us back there, and is right here, or you can use the one with the words, but x minus mu over sigma. So x is 2 minus the mu is -1 over the sigma, which is 2. So grab your calculator, find that value. 2 minus a -1, so that's 2 plus 1 is 3. 3 divided by 2 is going to give us 1.5. So you could stop there. You can just use the formula if you'd like. But again, as I mentioned, I like to check with a little bit of a sketch to see what's happening here. So if we were to sketch this curve and think about it as it is right now, it said that the mean was -1, the standard deviation was 2. So we're going to do a quick sketch here. This gets me, we're going to add 2, add 2, add 2, and then moving to the left, subtract 2, subtract 2, subtract 2. Now, underneath here, I'm going to list the z-scores. So the z-scores that match with each of these data values, that would be -3, -2, -1, 0, 1, 2, and 3. So again, going back to the problem, if we find the data value x equals 2, that's going to be right here. Notice that falls right in between the z-scores of 1 and 2. So I could say, yep, that looks good. 1.5 is reasonable and makes sense. Now, you don't always have to draw a little picture. I'm going to draw some quick sketches as we're going through the notes, again, just for anyone who's kind of visual. If you want to fast forward through that part while I'm drawing my sketches, if you are going to stick with the formula, that's perfectly fine. Let's move on to the next. Suppose a variable, again, is approximately normally distributed with a mean 12 and a standard deviation 6. What is the z-score of x equals 2? So once again, we have our mean, we have our standard deviation, and we have our x value. So using our formula, z is going to be x minus 12. I guess I didn't really need parentheses there, but we'll just throw them in there, divided by 6. So notice for this one, our z-score is going to be negative. So grab your calculator, and again, up here we were told we're going to round to the nearest hundredth for these. So when you find your value there, negative 1.67 would be our z-score. So again, I'm not going to draw all of the curve this time, but I'm just going to think about where this value is that I'm looking for, x equals 2. So if the mean was 12, then the data point x equals 2 is somewhere along this side. So just to, shorten up and be a little bit more efficient, I'm not going to worry about the numbers over here because those are not part of this problem. So if we were to kind of look, though, at our standard deviation is 6, so we subtract 6 from 12, we get 6. Subtract another 6, we get 0. This value I'm looking for is 2, which is about right here. So now we can think about our z-scores just on that side. So as I'm showing you here, this up here I did every single part. I showed the whole entire standard curve. I put all the standard deviations in. You can make it a little bit more efficient, a little more chopped down if you choose. So again, though, if we look at our standard deviations, our z-scores, underneath 12, 12 has a z-score of 0, 6 has a z-score of -1, 0 has a z-score of -2. So again, if we look to see where this data value falls, it's between -1 and -2, closer to -2. And you could even break it down further and figure out, how many units are between 6 and 0 and really break it down into thirds, and you can get that 2/3 piece that we're looking for in 1.67. But again, once you use the formula, you should be all set to go. Let's look at number 12. Suppose a variable, again, is normally distributed with a mean 9 and a standard deviation 3. So there's my mean, there's my standard deviation. What's the z-score of x equals 9? So this is one where if you stop and think before you do any computation, you should be able to answer this question. You shouldn't even have to put anything into the formula. Sometimes we don't recognize it right away, and if you do put it in and I will put it in the formula in a moment here, but if you stop and read this carefully, this variable has a mean of 9, and we're looking for the z-score of 9. If you go back to the standard normal curve at the top of our page, the mean is always right there in the center. It has a z-score of 0. So if you didn't catch that right away, because again, sometimes we start reading fast, we just want to put numbers into formulas. It happens. That's totally reasonable. But if you didn't notice it right away, you'd start with your formula here. The x value is 9 minus the mean, which is 9, divided by the standard deviation of 3. 9 minus 9 is 0, divided by 3 is 0. And again, if we drew the curve, it might be a little bit silly, but we'd have right here in the middle, we'd have 9. Well, that's the value I'm looking for, is 9. So again, z-score for the mean right in the center there is 0. All right, number 13. Suppose a normal distribution has a mean of 6 and a standard deviation of 1.5. So here's my mean and my standard deviation. What is the z-score of x equals 5.5? So we've been doing the formula first. You could also do a quick sketch first and sort of give yourself an idea of where this answer is going to fall. Again, just different ways for different folks to kind of problem solve here. The mean is 6. We're going for the z-score of 5.5. So again, instead of filling in all of the values all the way across this horizontal axis here, I know I just need to move to the left. And I'm going to the left, subtracting 1.5 as I go. So one standard deviation to the left is going to be 4.5. I don't have to go any further. I could keep going, but my value I'm looking for, again, is 5.5. So it's going to be somewhere in this vicinity here. So this is 5.5. And again, if we look at our z-scores, the 6 is the mean. We know that the mean always has a z-score of 0. And then one standard deviation below that would have a z-score of -1. So again, we look and see where does this kind of fit in to that little scale, and it looks like it's somewhere between -1 and 0, closer to 0, definitely a negative value though. So as we go back and we grab our formula, and some of you might even, just depending on, again, how your particular brain works, you might be able to almost picture this in your head and not even have to draw the whole thing out. But if you like to see the picture there like I do, it doesn't take too long to draw a quick sketch. So let's plug into the formula now and get the exact value here. So the x value is 5.5 minus the mean, which is 6, over the standard deviation, which is 1.5. Again, rounding to the nearest hundredth, we're going to get -0.33. And again, if I go back to my sketch, certainly looks like that fits in with the picture that we created previously. All right, let's keep going. take a look at the next example. In a normal distribution, x equals 5 has a z-score of negative 1.25. So this is more, these next couple of examples are more along the lines of just definition-wise, making sure you understand what you're being told, if you're being told about a mean and a z-score and that sort of stuff. So if the data value is 5 and it has a z-score of negative 1.25, that tells you that x is blank standard deviations to the blank of the mean. So the first part is just the distance. How far away is this data value from the mean? Well, we'll just look at the numerical part here, kind of the absolute value of our z-score. So it's 1.25 standard deviations. And then the second blank is our direction. Is it going to be to the left or to the right? So since we have a negative value here, this is going to be to the left of the mean. So the next two follow the same idea. In a normal distribution, x equals 3 has a z-score of, now it's positive, so note that, 0.67. This tells you that that data value x equals 3 is, and again we use the absolute value, just the distance, the magnitude of that z-score, 0.67 standard deviations. And then because it was positive, we know that that was to the right of the mean. Our positive z-scores are to the right, 1, 2, 3. Negative z-scores to the left, negative 1, negative 2, negative 3. 16. In a normal distribution, x equals 6 has a z-score of negative 1.7. So that means x equals 6 is 1.7 standard deviations to the left of the mean. Looking at that negative sign right there. So same as up here, right? So let's look at a few applications. Number 17 says, the life of Sunshine DVD players is normally distributed with a mean of 4.1 years and a standard deviation of 1.3 years. A DVD player is guaranteed for 3 years. We are interested in the length of time a DVD player lasts. So find the z-score corresponding to the guaranteed life of 3 years. Round to the nearest hundredth. All right, so again, we have a couple of different ways we can work through this. I'm going to start with the formula and then verify with a quick little sketch. So we know that we have our mean listed here, 4.1 years. That's the average lifespan of these DVD players. The standard deviation is 1.3 years. And we're looking for the z-score corresponding to the guaranteed life of 3 years. That is our x value. That's our data value we're looking for. And we're going to round to the nearest hundredth. So plugging into the z-score formula, we have x minus mu, the data value minus the mean, divided by the standard deviation. Find that on your calculator, round to the nearest hundredth, and we get negative 0.85. Should make sense that it's negative. If you can think about the mean is at 4.1, the data value is below that. So, okay, first things first, yes, the sign makes sense. Again, if you wanted to do a quick check with a quick little picture, we'd have 4.1 here. Again, we know we're going to 3, the data value of 3, so we need to go to the left. So if I go 1 standard deviation to the left, 4.1 minus 1.3, I'm going to get 2.8. So my value of 3 is somewhere in there. That's where x is equal to 3. So again, we can come down here and say my z-scores, the mean is always 0. This is at negative 1. Come on down here. Our z-score is almost to negative 1. So again, we can look back at this and say, yes, I think that seems like a reasonable answer. So let's look at 18. One more example here. The systolic blood pressure is given in millimeters of males, has an approximately normal distribution with mean 125 and standard deviation 14. Systolic blood pressure for males follows a normal distribution. So I'm going to start in this little space we have here by just drawing a quick curve and labeling it again as we've been doing. So normal, or the mean is 125. And the standard deviation is 14. So moving to the right, we're going to add 14, 139, and then we get 153. 167. Moving to the left, subtracting 14 each time, we're at 111, 97, and then 83. So the question asks us in part A to calculate the z-scores for the male systolic blood pressures 100 and 150 millimeters. So 100 is going to be right in here, roughly. And 150 would be over here. So we're going to calculate, so we can kind of get a little guesstimate going here. The z-score for 97 is -2. I've got to kind of squeeze it in there. And then the z-score of 111 is -1. So we know we're in between -1, -2. And then over there for 150, we're in between +1 and +2. So let's use our formula to calculate each of these. So z is equal to 100 minus 125 divided by 14. Rounding to the nearest hundredth again, we'll get -1.79. Again, if you want to just practice with your calculator, you can always pause on any of these calculations. I have my answers already written down and ready to go, so I'm not having to work through the calculator work. But you should definitely make sure that you're getting the same answers that way. So next, we're doing 150. So the z-score is 150 minus 125 divided by 14. And that gives us positive 1.79. If you look back at my sketch there, you can see the symmetry there, that both of those values were 3 values inside of the -2 z-score and the +2 z-score, so it should kind of make sense that they match up being opposites of one another. So the last part just asks us to kind of think about this and analyze it a little bit. So if a male friend of yours said he thought his systolic blood pressure was 2.5 standard deviations below the mean, so they're below the mean, let's think about where that would be. So -2, so going to the left here, 2 standard deviations below is at 97, so somewhere like that. That value in between 97 and 83, that says that's he believes his blood pressure was between 100 and 150, so in this range here that we were looking at. What would you say to him? Well, basically I would say to him, he's incorrect. Now, mathematically, you might be asked, well, how do you know? Why are you telling me that? So that's where you could use your data to kind of back it up. If your blood pressure is 2.5 standard deviations below the mean, you could explain a couple different things. You could say, well, then it has to be between 83 and 97. Or you could go back to the information that we found in part A and say, if your blood pressure is, if you believe it's between 100 and 150, that's from -1.79 to +1.79 standard deviation, so or within those z-scores. So you could explain it a couple of different ways, looking at using the numbers and mathematics to kind of prove your point. I hope this video has been helpful for you.